Hello ladies and gentlemen, and welcome back to another measurement cast. This time I'm going to present a paper who I should have presented at AMPS on 29th of September, that is in 3 days, but unfortunately I won't be able to make it and none of the authors will be able to make it. Therefore, I want to give big thanks to Professor Mihail Albu for kindly agreeing to present this on our behalf at the conference. And since I cannot go there and present it, I will just go ahead and present it here. So the paper name is paper title is development of a flexible laboratory testing platform for assessing steady state and transient performance of WAMPs. So our motivation was to develop this flexible testing system was the need to test against a wide range of signals. I mean, you have in the standard, you have so many signals defined for steady state and transient step test, plus 10%, plus 90 degrees, minus 90 degrees. Then you have steps of amplitudes, 10%, 20%, and so on and so forth. Then the idea was to, I mean, the final goal was to get to the inter-area oscillations. So we started by modeling electromechanical oscillations to mathematical equations, and it would have been really handy to have a system that could generate a signal model by a mathematical equation just like that. And also, in order to be able to generate real power system signals, we had to develop some models in Dixieland, more specifically the two-area system of Kundur, in order to be able to get our hands on these inter-area oscillations. Then there was the need to perform numerous tests, obviously, in order to perform a rigorous assessment of one's performance, and also to include the phasor data concentrator, because you kind of feed some input signals, get the data, do some fancy analysis with it, and at the end of the day, what's the role of the phasor data concentrator? I mean, you can do it offline, you can do it after 1 day, 2 days. So we will see later how this will come into play. So the solutions that we implemented to address the problems I have just described is to use signal generators, which were capable of basically reproducing any signal described by an external file. So I needed, for example, we haven't done it, we could have, with the equipment used, we could have imported some data acquired from a real network and run it into our experimental setup. We used two Omicron signal generators for that, and with relatively high accuracy, they could generate whatever signals we were able to write into the ComTrade file standard. That was the format. Into the ComTrade file format. That was the format the signal generators were using. Then we developed a MATLAB library capable of generating any sort of transient for every test described in the standard. There is a function within the library which generates the ComTrade file, which you can just run into the experimental setup and get the testing going. And also, you remember that phasor data concentrator idea that I was telling you. So I automated the process of acquisition of extracting data from the phasor data concentrator and analyze it on the fly. So this is going towards the online estimation of inter-area oscillations. And then again, you have some delay, which is inserted from the phasor data concentrator. You make some estimations, take some decisions based on those estimations, but the decisions you make are for 1 second ago or 2 seconds ago. There are some uncertainties. I mean, you cannot say I absolutely need to do that. So we haven't actually done that. It's a work in progress, but I have done. I mean, I have automated the acquisition and the analysis procedure and the estimation of inter-area oscillations. So let's have a look at the experimental setup. Really simple figure here. The data source, which are the simulations, and they produce COMTRADE files which go into the signal generators, the Omicron test station, which basically each one of them is connected to one PMU, so we can simulate two buses within any network simulated in Dixilent, and the PMUs through a LAN go to the concentrator, and then my libraries take the output from the concentrator and make the analysis, compare it with the simulations, and come up with some indicators. Now this is a detailed view. What is here to see is that you have from the Dixilent simulation, for example, you get the COMTRADE files which go into Omicron. There are two PMUs, two Omicron, so all the thing is symmetric. Everything goes into the phaser concentrator, and post-processing compares the simulations, which are not only Dixilent, they're also MATLAB, and produces this total vector error and estimation of inter-area oscillations. We will have at the end snapshot of the real experimental setup. So the first important part of our work has been the generation of input signals, just because in order to achieve that flexibility, we needed the COMTRADE format in order for the Omicrons to work, to generate what we wanted. So there was a readily available COMTRADE functionality in Dixilent. I could just export in COMTRADE the signals simulated at a particular bus, but that was not straightforward. Anyways, I had to actually extract the data from the COMTRADE file and write it again into the COMTRADE file, just because there are some, they say it's a standard, but I mean, Dixilent and COMTRADE, I mean, for example, the Omicrons, they could not read the COMTRADE exported by Dixilent. So I had to extract data from Dixilent and write it again with a MATLAB function. So the developed from scratch COMTRADE functionality in MATLAB came in quite handy. And the reason I've used both MATLAB and Dixilent is just because MATLAB is very well suited for ideal math model signals. You want to use an equation describing an electromechanical oscillation. That's where you should do it. You have full control over the output signal, whereas Dixilent is suited for real transients. So you have real generators, real inertia constants, so many parameters in the dynamic models of the generators. It's crazy. It's so hard to generate an ideal signal with Dixilent, for example, but it is suited for anything else. So MATLAB library, which I called SIGGEN, and in Dixilent the input signal has been the implementation of two-area system, and we have varied some parameters there. We'll get there in a moment. This is an overview of the SIGGEN library, and these are the final test sets on which mainly the final conclusions have been drawn, but these test sets have been repeated at least 10 or 11 times, to say the least. You have, let's look at the categories: steady state functions for both current and voltage, transient step, it's basically amplitude, frequency, and phase step, oscillations, which you can superimpose an oscillation on top of a sinusoid. You can specify the amplitude and the frequency, and also ramp, which is amplitude ramp, frequency ramp, and phase ramp, which are, so to say, multiple step tests. They are not actually ramp, they are multiple step tests. So this is only for programming purposes, bureaucratic purposes, you name it. So let's have a look at the VOSC function, which generates an amplitude modulated signal described by this equation. This is basically the modulation part, which comes on top of the amplitude, and the damping is 0 because you have an ongoing constant amplitude, constant frequency oscillation. And let's see how VOSC function works. And as you can see here, I have the library with all these M files. You remember the table with the functions 2 slides back. And all I have to do is write VOSC, specify the parameters, which are amplitude, frequency, duration of test. 0.1 is the percentage from the amplitude of the superimposed oscillation, and 1 is the frequency of the oscillation. As you can see here, these oscillation occurring, and this is what happens in the front end. So you see what you have generated, but in the back end, what is most important, a COM-trade file is generated, which you can see here, and you can see much more clearly. I've used a COM-trade file viewer, and I've used it to see exactly the phasors at basically each moment in time. So this COM-trade file is really important. Now you are ready to do the testing. You can load it into the Omicrons, and you have you get the necessary data into the PDC, and you can compare it with the simulation. Now for Dick Silent, there has been an implementation of the two-area system from Kunder, and the idea was to generate different frequency and damping of inter-area oscillations by varying the tie-line flow. And how do you vary the tie-line flow? Basically, you go into one area, let's say the right area, this load has been modified, and if you modify this load, automatically the power that goes from one area to the other is modified. Therefore you get different parameters for the oscillations between these two areas. And what I did was to extract the signals at bus 3 and bus 13, apply an estimation, to be more specific, a Prony estimation on the angle difference, because as you know, the angle difference is directly proportional to the power transfer, and compare these frequencies and damping of inter-area oscillations, compare them with the same parameters estimated within Dick Silent by using model analysis, which is, let's say, this was the indicator that my estimation was good. Now we are done with the signal generators. Let's have a look at the data acquisition, because this is actually really important. So the PDC is the main driver of the acquisition system. You have the MATLAB and Dick Silent simulation. They go into the COM-trade file, into the signal generators. Then the PMUs measure the phasors, and they dump them into the phasor data concentrator. But how do you extract data from here? Now you can have, for example, SPDC, which is the proprietary PDC delivered together with the two PMUs, and you can start and stop the acquisition process. Then you can click for the millionth time, click browse, locate the latest archive location, and click export. There are a zillion of clicks that you need to do, and you can only limit yourself to an offline assessment of the performance of the PMUs this way, because doing it manually, there is no way you could actually use that data to make some decisions.